What is going on, guys? Welcome back. In this video today we're going to build a movie recommender system using a large language model and a vector store in Python. So let us get right into it. Alright, so we're going to build a movie recommender system in Python today, which is going to be powered by a large language model which runs locally on our machine. Now I'm going to give you a brief sketch of the process so that you understand how the recommendation process works and you don't have to just copy paste the code without understanding what it does. So it's not going to be the most beautiful sketch here, but I'm going to try to explain it as simply as possible. What we're going to do is we're going to work with a dataset from Kaggle, and this is going to be a Netflix dataset containing information about TV shows and movies, and it has features like title of the movie or show and description and cast and release year and genre and so on. So each row represents a movie or a TV show and has features like the type, is it a movie or TV show, stuff like the title and the description and the release year and the director and the cast and so on. So we have a couple of features here per row. And what we want to do now is we want to take these and turn them into a textual representation. Now, this is quite simple. We don't have to do anything else but just create a string that says something like type is whatever, for example, movie. Then title is whatever the title of the movie is and so on. And all of this is going to be one large string containing all the information about that movie. Now, what our large language model will do with that string is it will take this string and it will embed it into vector space. To keep it simple, this basically means that the large language model does something with this content, with this string, and turns it into a vector, into a high dimensional vector. To be precise, we're going to use Llama 2 in this video, locally here, and Llama 2 will produce a vector for each row with the size 4096. So we're going to have 4096 different values here, numbers, that will position this vector in the vector space, in the 4096 dimensional vector space. This is what we're going to do here. So every movie will end up being some point in this vector space, some vector in this vector space. Now, the idea is that similar movies or movies that are somehow similar to one another will end up closer in the vector space than movies that are very different. Now, how does it happen? That's the intelligence of Llama 2. So we don't have to do any fancy coding here. We don't have to implement some intelligent algorithm. We don't have to train a machine learning model. We expect Llama 2 to have the intelligence. This is already inside of the model, the intelligence needed to do that, to take movies that are somewhat similar and to put them together, closer together in the vector space than movies that are completely different. That's the basic idea. And then what we do is we store all of these vectors into a vector store, so a vector database. We're going to use FACE, which is a Facebook. I don't know what the acronym is, but it's a vector store by Facebook. And this vector store will contain all the different vectors. And what we can do then with this vector store is we get some new movie with the string title and type and director and so on as a string. We feed this into the index, into our vector store. And as a result, we get, for example, the top 5 most similar movies that could be interesting to you if you like this one. So you get a list of 5 movies that could be interesting to you. That is what we're going to build in this video today, using Llama 2 running on our system locally, if you can do that. Otherwise, you will probably have to host it somewhere, or you have to use the API of something else. You can also use ChatGPT, but you have to pay for it, or actually just GPT, not ChatGPT. But if you have the resources, you can just run this locally using Ollama. So this is what we're going to build in this video today. Now, how are we going to do that? We're going to start by, first of all, installing Ollama. Now, Ollama is quite easy to install. You just go to the website, ollama.com. You download it for your operating system. On Linux, you just run this command, and then you can use it on your system. If you have troubles with that, I have a video on this channel about Ollama where you can look, where you can see how I install it and how it works, basically. But it's really not complicated. What we're going to do then is, once you have Ollama installed, you're going to type into your terminal Ollama pull, and then the model that you want to use. As I said, I'm going to use Llama 2. You can also provide another model name. I think on their website, you should be able to see the models that they offer. You have Llama 3, you have Mistral, you have Llama 2 with the different parameters also as well if you want to have a larger model. But you can do that and install the model that you want to use. All right. So once you have that done, we're going to also download a dataset from Kaggle, the Netflix movies and TV shows dataset. You will find a link in the description down below. Just download the Netflix titles CSV file, and then we can get started with the coding. Now, actually, before we get started with the coding, we also need to install the Python packages that we're going to use in this video. And for this, we're going to open up a command line and install NumPy, pandas, face, and requests. These are the 4 packages that we're going to need in this video today. NumPy and pandas, obviously, because we're going to work with data. Face, because that is our vector store. And requests, because we need to send requests to Ollama. Now, actually, we cannot say face. I think we need to say face CPU or face GPU. So depending on whether you have a GPU that you can use here, run face GPU or face CPU if you want to use your processor for this. Just install the packages, and once you have them, we can get started. All right, so the first thing is we're going to obviously import pandas as PD, and we're going to then say the data frame is going to be PD read CSV Netflix titles CSV. And then we can look at it, and you can see we have, let me just close this here. We have a couple of features, the idea of the show, we have the type of the show, movie or TV show, we have the title, we have the director, the cast, the country that it was produced in, I guess, the date it was added to Netflix, the release year, also some rating, the duration, and also the genres here. So what kind of movie is it? And the most important thing, I assume, is going to be the description, because it tells us briefly what the movie is about. And I think that's the most important thing, maybe together with the documentaries and with a cast, that is going to be relevant for a similarity search. All right, so we're going to keep it simple here. All we're going to do is we're going to craft for each line a string that represents this, or the individual movies, textually. So we're going to create a function down here. We're going to call it def, we're going to call it create textual representation given a row from the data frame. And what we're going to do is we're going to say textual representation is going to be equal to a multi-line string like this. And the important thing is to not have any tabs here. And we're going to say something like type, and type is going to be just row. Actually, we need to make this a formatted multi-line string like this. The type is going to be the type. Then we're going to say that the title is going to be the title, and actually we can then just go and copy paste this, I think, and we can say we want to have the director, we want to have the cast, and we want to have the release year and the genres, and the most important thing also in the end, the description. So this is going to be description, this is going to be genre. Actually, we need to turn this into row title and into row director and into row cast and into row release, I think release year, right? And into row, and I think it was, what was it called? Listed in is what we're looking for. Listed in. And then finally, of course, row description. So that should work. And this function now applied to the rows, and we're going to do it like this here. This function applied, of course, we need to return the textual representation. This function now applied to the individual rows will give us textual representations for the individual rows. So I can say df apply, and then I can just apply the create textual representation function, axis equals 1, and I will get for every single row here, I will get the string. So I can say actually that this is my textual representation column. Then you can see I have it, and then I can just get the column and show the different values. So if I print the first one, we're going to see that this is what this looks like in the end. So this is just our basic representation now, which we're going to use to ask Llama 2 to turn this into a vector into vector space, or in the vector space. So what we're going to do next is we're going to say import face, our vector store, import requests so that we can send requests to Llama 2 or to OLlama, and import numpy as np. We're going to need this here to create the array for our vector store. We're going to define the dimension of our output, as I said, to be 4096, because that is what is going to be returned by Llama 2 for the embedding dimensions. We're going to say index is equal to face index flat L2 with the dimension here as a parameter. This is basically our database, you could say, our vector store that we're creating. And then we're going to initialize an x full of zeros. And the dimensions here are going to be the length of the textual representations. So how many instances do we have? How many movies or shows do we have? And how large is the dimension for each of them? So we're going to have n vectors here, this amount of vectors of size dimension. And the data type is going to be float 32. All right, so that is now an array full of zeros, as you can see, and this is going to be filled up with the embeddings from Llama 2. So we're going to say now for I row in, or actually for I representation in enumerate data frame textual representation. What we want to do is we want to say if I is 200, or not 200, if I is divisible by 200, so every 200 rows, I want to print the progress so I know how long it takes. I'm not going to run all of this on camera because it's going to take quite some time, but you can run this here to see the progress. Just say something like processed, and then I, and then processed I, CRI instances, for example. And then we're going to say that I want to send a request, which is going to return a response. So res is equal to request. I want to send a post request to OLlama, and OLlama by default, unless you change that, is running at HTTP and then localhost port 11434. So 11434 is the port that OLlama is running at. And we want to use the embeddings API. So /API/embeddings. And what we want to send to this API is a JSON object. And this JSON object will contain the model that we want to use. So the model is going to be Llama 2. And also the prompt that we want to use, or the prompt that should be embedded. So the prompt is going to be equal to the representation that we're currently at. There you go. And this needs to be closed like this. Actually, this should be indented. Yeah, let's just leave it like this. And this is going to return a response, and this response will have a field embedding. So we want to say embedding is equal to the response, get me the JSON object from the response, and what I'm interested in is the field embedding. This embedding is the vector. So all we have to do now is we have to go to the ith position. This is why we enumerate this. We're going to want to go to the ith position in our 0 vector, and we want to replace the zeros with this new embedding that we got from the large language model. So np array embedding. And then finally, in the end, we can add all of x to our vector store. Now, I will turn this number down to, let's say, 30, so that you can see how fast this works. We have, remember, 8,807 rows to be processed. And if I run this, you can see that it isn't that fast. Actually, now I need to check that this is equal to 0. And then I can run this again. Process 0 instances. Then it takes some time, process 30 instances and so on. I think my video is lagging. I'm pretty sure my video was lagging while this was running because it was running on the GPU. So I'm not going to run this here on camera. What I have actually done is I have trained this already, and I will show you how you can save this when you've trained this already. So you run this, you wait for it to finish, and once it's finished, what you do is you say face write index, and then you just take the index, so this object here that you created, and you write it to a file. For example, let's call it index as well. Once you do that, you're going to create a file index that contains the index. So you only have to run this once, then it's done, and then you can use it because you now have a vector database full of embeddings for the different movies. And in order to load it then, which is what I'm going to do now, in order to load it again, you just need to go and say, index is equal to face read index and then the file. For example, index. And this is what I'm going to do here now. So now I just copy pasted the exported vector store, the index file from my prepared code. And all I have to do now is I have to open up a new cell and say that the index is equal to face read index. And then I just have to provide index. And then I can go ahead and use this index to do a similarity search. So how exactly can I now recommend a movie based on another movie? Now, first of all, I can craft my own textual representation of whatever movie I like. I don't have to use a movie that's already part of the data frame, but let's start with a movie that's part of the data frame. So what I can do, for example, is I can say one of my favorite movies is Shutter Island. I want to see if that's part of the data frame. So let's go and say df, where df title string contains, and let's see if we have Shutter Island in here. And in this case, we have the movie Shutter and we have the movie Shutter Island. So let's copy this ID. And let's say that what I want to use now here as a base for my recommendation is my favorite movie is actually df iloc and then this. So we can see that my favorite movie is Shutter Island here. And now I can just go ahead and I can get the, or actually let's go and write the code directly. What we need to do now is we need to send this movie to Ollama to be embedded. Now we're going to pretend that this movie is not already embedded, so we're not going to use it directly. We're going to actually embed it again because this is now our new movie that we passed to the recommender system here, and we want it to be embedded into the vector space, and then it should find the most similar movie, so the closest embeddings to the embeddings or to the embedding of this particular movie. So what we do is we say response equals requests dot post, and we post to the same URL. So localhost port 11434 /API embeddings, and then we want to say that the JSON is going to be equal to a dictionary, and the content here is going to be model again llama 2, and the prompt in this case is going to be our favorite movie, and from it the textual representation like this. That is going to be our request that we sent here, and this is going to result in a embedding. So we're going to get the embedding from this response. Again, get the JSON object, get the embedding, and actually we need to do some additional processing. So we're going to say here, we're going to turn this into a NumPy array. That's just some formatting stuff here. So we're going to say it's a NumPy array of a list of the embedding with the data type float32. And this is now what we're going to use as a basis for the similarity search. So we're going to search our index for similar embeddings to this one. So we're going to say D and I is equal to index search. Given the embedding, give me the top 5 matches. So I can say 5 here, and this will result in the top 5 matches. Now, what I'm going to get here as a response is, of course, not the actual title, not the actual data, not the textual representation. I will get the indices. I will get the actual, we can look at it. I will get the numbers. I will not get any specific movies. So what I have to do is I have to take the data frame and get these particular movies. So what I can do is I can say the best matches are going to be equal to NP array and then data frame textual representation. And from this, we're gonna go and get I flatten, get all these indices, flatten them, and use them as an index here. And then I can just say for a match in best matches, I want to print next movie. Then I want to print the match, so the movie representation, and then just an empty line. And this is going to give me the top 5 recommendations. Now, obviously, the most similar match here to my prompt, to my embedding, is the embedding itself, because Shutter Island was already part of the vector store. So, of course, the closest match is Shutter Island itself. The second closest one is this one, Devil's Gate. Seeking a missing woman in North Dakota, an FBI agent and a sheriff focus on her religious zealot husband, but discovers something far more sinister. Sounds like something mysterious and something slightly scary, which is also a little bit like Shutter Island. I've not watched this movie, but I think that could be a good match, at least from the description, it sounds like that. And then you can also see the other matches here. Now, the interesting thing is I don't have to provide actually an existing movie. I can also make up a movie. I can maybe say I can imagine a movie. So let's go and copy this. And let's turn this into a string. And let's just make up something. So let's say my title, my movie title is The Mysterious Python. The director is, who did Shutter Island? Let's use the same director. And then let's say the cast is Leonardo DiCaprio. And then maybe, I don't know, let's go with someone else like Sylvester. Is it written like this, Stallone? I hope so. I hope this is not too embarrassing. I'm not a movies guy, so I don't know. Let's just say these are the 2 people, and then it's released 2020, and it's mystery, drama, thriller, or something like this. And then we can say that the description is a group of adventurers discover a mysterious programming snake in the jungle, and I don't know, and find something extremely shocking. Yeah, let's say this is my movie description now. I can take this and I can actually save this now as representation. And then I can use that as an input here, representation. And then I get the embeddings, and the best matches are the following. A patch of fog. This is when a guard catches a writer television host shoplifting. Instead of turning him in, he only asks to be a friend, then begins to rule his life. Okay, I don't know why that is super similar to what I said. But yeah, I mean, you can play around with that and see how good the recommendations are. Maybe it's also reasonable to only include the description, or to only include genres in description, something like this. Maybe the other things are too confusing. But that's the basic idea. This is how you can build a recommender system based on any data set. You just pick a textual representation, or you create a textual representation, you embed these representations, and then you just perform a similarity search. And you hope that the embeddings are somewhat intelligent based on the large language model that you use to create them. So that's it for today's video. I hope you enjoyed it and I hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.